This is 2.6, rational functions. Below this slide, I don't want you to write down these items. The first thing is just explaining what a rational function looks like. It is a polynomial in the numerator divided by a polynomial in the denominator. Don't need to write that down. We covered these in Algebra 2 in Chapter 8. What the graphs will look like are something like this, where you're going to have vertical, horizontal, slant asymptotes that will help guide those curves, and you might have a hole in the graph, etc. So here is what a function would look like as a rational. Then there are multi-steps that we're going to go through. I don't want you to write these down. We're going to go through 2 of them today in class. So I kind of follow a certain order. I say identify the domain of the function. So you set the denominator not equal to 0 and solve for x. Then the vertical asymptote, the VA for short, is where those domain restrictions are. Then there are possible horizontal or slant asymptotes. So I do that as step 3. And I'm looking at the degree of the numerator over the degree of the denominator. If the numerator is greater than the denominator, then you have a slant or a horizontal at y equals 0. If the degrees are the same of the numerator and denominator, then you have a horizontal asymptote when you divide the coefficients. If the numerator is greater than the denominator, then you don't have a horizontal asymptote, but you do need to check to see if there's a slant. And slant asymptotes only occur when the degree of the numerator is 1 more than the degree of the denominator. And we will use long division to find that slant equation. It'll be in the form y equals mx plus b. And you're going to ignore the remainder. So we're going to show you an example of this today as one of our 2 examples. Then we would move on to finding the x-intercepts. Again, don't need to write these down. The x-intercepts are the zeros of the numerator. To find the y-intercept, we set the x equal to 0 in the function. You're evaluating the function for 0 and solving for y. And then you're going to test for symmetry, which we did earlier in our class. Those are the rules to test for symmetry. And then maybe need to plot some additional points by evaluating the function, making an XY chart. Here's what I do want you to write down is this example. I've broken down the problem into all of those steps identified out. And on Class Jump, this video will be out here too, and also as a PDF. So if you want all the rules printed out, maybe you want to do that as a PDF, print out the first couple of slides. All right. So what we're going to do is we're going to graph this rational function. The numerator has a polynomial of 2x squared. The denominator has a polynomial of x squared minus 1. And we want to graph out this polynomial function, the rational function, with all the important key items. So I just start with the domain. And I find out what would make it undefined, what would make that denominator 0. And those are where your domain restrictions will be. So I'm going to set this denominator not equal to 0. And then I solve for x. You can solve by undoing, or you can factor it in this problem. So how would I factor x squared minus 1? How do I factor that? There's 2 terms. They're both squared. Yep, difference of 2 squared. It's x minus 1 and x plus 1. And then I would solve that. So I would get x equals 1, x equals negative 1. So the domain would then be all of the numbers in the real number system except for those two. So the domain then is all reals except x can't be 1 or x can't be -1. So since that's my domain restrictions, my x value domain restrictions, then I cannot have ordered pairs on that x vertical asymptote. So those are your vertical asymptotes then. So that's why I do the next thing is identify the vertical asymptotes. So then your vertical asymptotes are at those domain restrictions. So x equals 1 and x equals -1. Give you some time to write. Yep, so whatever your domain restrictions are, those are where your vertical asymptotes will be. When you set the denominator equal to 0 and you solve for x, the 0 is of the denominator. Then the next thing I do is I go out and find if there's a horizontal asymptote or a slant asymptote. And I'm looking at the degrees of the numerator and the denominator when I'm checking for a horizontal. So let's go back to the problem. This is my numerator. What's the degree of the numerator? 2. The degree of this one is 2. What's the degree of the denominator? It's also 2. So both the degrees are the same in the numerator and the denominator. So the rule is, then you divide by their coefficients. So the coefficient of the numerator is 2. What's the coefficient of the denominator? 1. So you divide those two numbers. And that's what this is saying here. You take the leading coefficient of the numerator and the denominator. So you take 2 over 1. So y equals 2 is where you'll have a horizontal asymptote. There's two other scenarios that are on that first slide set underneath the steps. If the numerator is greater than the denominator, or if the numerator is smaller than the denominator, what would happen? And they're out there on that slide. If there was a slant, it would look something like this. An x cubed over an x squared. It'd be exactly 1 more than the denominator, which it's not. So there's not a slant. Let's erase that. All right. Now let's move on to step 4. So step 4 is I go out and find the x-intercepts. So remember from earlier in our class in chapter 2, the x-intercepts exist at the zeros of the function. In this case, we're only looking at the numerator. So we're only looking at the 2x squared. So the numerator was 2x squared. We find the zeros of that numerator. So we solve it for x. So we would first divide by 2. Reduce it. Then solve for x. So you would square root both sides. and you get x equals 0 and 0. I have two zeros at 0. Those are called repeated zeros, multiplicity of 2. So our x-intercept is at 0, 0. I'll do the y-intercept and then I'm going to stop the video. Step 5 is I go out and find the y-intercept. So for the y-intercept, I evaluate the function for x. And I'm letting x equal 0 and solve for y. So y equals 2x squared over x squared minus 1. I would substitute 0 in for x. So 2 times 0 squared over 0 squared minus 1. I get 0 over negative 1, which is 0. Which makes sense because there was my x-intercept of 0, 0. So my y-intercept is also at 0, 0. We'll continue this problem on the next video.